Hi everyone, this is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College Women, Nalgonda. Now I am going to present my lecture, Gauss Law. This is the part of Electrostatics. This is in the syllabus of BSc final year, 5th semester Electromagnetism. The plan of my lecture is Introduction, the basic concepts of electric flux. Then we will discuss about the Gauss Law and its explanation. Then after, we will derive the integral form of Gauss law. Then after, differential form of Gauss law and deriving the Coulomb's inverse square law using the Gauss law and Gauss law importance. Lastly, we'll see the summary points. Yes. Now, under the introduction, let us see first the concept of electric flux. What is the concept of electric flux? Electric flux is nothing but the number of electric lines of force passing through the given surface area. Okay. For example, I am considering the charge, point charge plus Q. Okay. So around this is a closed surface. So due to the point charge, positive charge, the electric lines of force moves away from the charge like this. Radially outward direction, the lines of force are moving. So this electric flux, we say that outward flux. Outward flux is always taken as positive. The inward flux taken as negative. So due to the flux of negative charge, the flux is inwards. The flux of positive charge is always positive. That is outward direction. Okay, right. Now, so now I consider a closed surface area about the point charge. Then the number of lines of force crossing through this closed surface area. That is nothing but electric flux through that closed surface. So here the surface, the shape of the surface may be regular or irregular. It doesn't depend on size and shape of the closed surface area. Right. So electric flux is defined as the total number of electric lines of force crossing through the closed surface area considered above the charge. Okay, right. Now I am considering the irregular shape closed surface. This is a closed surface. In this, a point charge plus Q is kept. Okay. Imagine that this closed surface is divided into very small infinitesimal area elements. Like this. Okay. Now I am taking one small area element. This is one small area element. Due to the point charge plus Q at this point P, the direction of field strength say in this direction, E bar direction. So this is the area element ds. Okay, small area element ds. The direction of this area element, that is nothing but outward unit vector to this surface area. What I am saying, where n cap is the outward normal unit vector to this surface area element. Suppose that angle between n cap and E bar is theta. Then the direction of this area element, we write it as ds bar is equal ds into n cap. Okay, ds is the magnitude of that area element. N cap is the unit vector or the direction of that area element. Okay. Yes. Now the flux through this surface. Now I am writing the electric flux through the area element ds is given by d phi is equal to suffix e equal to e bar dot ds. Okay, that equals to e ds cos theta. E ds cos theta. Understand the concept? Now the total closed surface area is divided to very small infinitesimal area element. I considered a small element ds. The direction of this ds is n cap direction. So angle between n cap and e bar is theta. Then how many number of lines of force are crossing this area? That is nothing but electric flux through this area element. So the electric flux through this area element is nothing but what? The number of lines of force crossing through this small area element. That is I am writing d phi. Okay. D phi equal to E bar dot ds bar, that equal to E ds bar. Right. Now there we have the many number of area elements. Then the total flux due to this point charge q. So the flux through all area elements is given by phi e is equal integral of over s d phi d phi. So the total flux to the total surface is equal integral over s d phi e bar dot ds bar, that equals to integral s e ds cos theta. Okay, e ds cos theta. I hope you understand. So electric flux is defined as the total number of lines of force, the total number of electric lines of force crossing through the given closed surface area. Right? The total flux through this surface area, as we have written, phi equal integral over s e bar dot ds bar, that equal integral of e ds cos theta. Right? Now, so here I am explaining this concept. Right? Suppose, yes, you see here. So finally, what we got? The total flux phi is equal to E integral over S E bar dot ds bar, that equal E ds cos theta. E ds cos theta. Now I am taking the uniform electric fields. This is the uniform electric field. So lines of force are parallel and equidistant. Okay. In this, suppose if you consider a closed surface like this, perpendicular to this field direction. Okay. Then what would be the outward unit vector direction n cap? That means n cap direction is perpendicular to this surface. Yes, whatever I consider the closed surface, that is perpendicular to the field direction, like this. So n cap direction that is parallel to the e bar. Hence the flux phi is equal to E ds cos theta. Here E ds cos 0 phi e equal to E into ds, since where theta equals to 0. N cap and E bar are in the same direction. Okay. Now I am taking an area A. Okay. Here the field direction is like this E bar. Right. The outward unit vector to the surface area N cap is also in the same direction. Same case. Right. Here N cap, E cap both are in the same direction. Theta equals to 0. Therefore, flux phi equal to E into Ts cos 0. E into the area we have taken A. E into E A cos 0. Hence, the total flux is equal to E into E. Here, unit vector is outward direction. So here the flux is coming outside. This is called outward flux. This is possible for positive charges. For positive charge, lines of force moving radial outwards. Then the unit vector also in the outward direction. We say that the flux is outward. The outward flux is always taken as positive. Okay. Now you see this figure. Okay. Here I am taking the field direction E bar. Okay. Now n cap direction is perpendicular to the surface inward direction. So E bar direction in this direction outside, n cap direction perpendicular to surface inward direction. Here theta equals to 180 degree. Then the flux through that surface E A cos of 180. Phi E is equal to E A cos 180 minus 1 minus E A. Right? Here flux we got minus sign. The flux is negative because here we consider the inward flux. This is the flux due to the negative charge. Flux due to the negative charge, since the lines of force are entering inside, the flux is we are getting negative sign. Okay. Suppose the area element, this one, E bar direction, field strength direction is like this, N cap direction is like this. Angle between N cap and theta E bar are 90 degrees. Okay. So then the flux phi is equal E A cos 90. That equals to get 0. Okay. When the area is parallel to the field, like this. So this is the closed surface area. I consider rectangular closed surface area. The field direction is right side. Now it is parallel to the field. Area is parallel to the field. Then the outward unit vector in this direction. N cap is in this direction. N cap direction perpendicular to the board plane. E bar direction is on the plane towards the right. So angle between N cap and E bar here 90 degrees. Then the flux through this surface, how much? 0. So it is very clear that when the area is parallel to the field or area is perpendicular to the field, when the area is parallel to the field, the flux is 0. Okay. When the area is perpendicular to the field, then N cap and E bar in the same direction, flux is max. Right? So this is about electric flux. So here, what we are saying, electric flux is nothing but the number of electric lines of force passing through the given closed surface area. There we are considering the number. Due to the 1 coulomb of charge, the flux is equal to 1 by epsilon naught. If you consider the q coulombs of charge, from that the number of lines will come out or will move inside equal to q by epsilon naught. Okay, so it is a scalar quantity. Electric flux is a scalar quantity because we are talking about the number of electric lines of force. Right, sir. Now, let us go for basing on this concept, using this electric flux concept. Now, I am going to talk about the Gauss law. This is the actual concept of present lecture. Gauss law. What is the Gauss law? Yes, I considered a point charge plus 2. So around this, again I considered a closed surface area, which is having some volume in the space, right? Since it is a point charge, class 2 charge, the lines of force will come out outside. So electric flux is outward direction, right? The electric flux coming out to this closed surface, the flux coming out through this closed surface area, whatever we considered, that is we are writing as phi E is equal integral over S E bar dot ds bar, that equals to 1 by epsilon naught times to the charge enclosed by that surface. This is the statement of Gauss law. Okay. The electric flux through the closed surface, around a charge is equal to 1 by epsilon naught times to the net charge enclosed by that surface. Here, if there is no charge, then Q equal to 0, the flux is 0 because there are no lines of force. Okay. Now I consider two charges. One is Q1 charge, another is plus Q2 charge. Due to the Q1 charge, the lines of force will come out like this in all directions. Due to the charge Q2 also, the lines of force will come out like this. So then what is the net charge in this enclosed surface? Then Q net is equals to the sum of those two charges, Q1 plus Q. Now, how we write the statement? Phi E equal integral over S, surface integral, E bar dot ds bar, that equals to 1 by epsilon naught into net charge Q1 plus Q2. I hope you understand. Okay. Now I consider three charges. One is Q1, another is plus Q2, the third charge minus Q. Okay. So here two positive charges, one is negative charge. Due to the positive charge, the the flux is outward. Due to the negative charge, the flux is always inward direction. This is the outward flux, it is inward flux. So what is the net charge enclosed by this closed surface? Q1 plus Q2 minus Q3. Now the flux, net flux, the total flux will come out through this closed surface is equal to surface integral E bar dot ds bar, that is called 1 by epsilon naught into net charge Q1 plus Q2 minus Q2. Okay. So in general, I am writing now the phi E is equal surface integral E bar dot ds bar, that is called 1 by epsilon naught times to the net charge. This is the Gauss law statement. So what I'm saying, the statement of Gauss law is the flux, the total flux to the closed surface, through the closed surface about the charge is equal to 1 by epsilon naught times to the net charge enclosed by that given closed surface. Right? This is the statement of Gauss. Right. Now, here, this Gauss law, what is the importance of this Gauss law? So, by using the symmetry concept, it is very easy to calculate electric field strength in the case of linear charge distribution, surface charge distribution, and volume charge distributions. For example, if you consider uniformly charged wire, infinite length of uniformly charged wire, uniformly charged plane sheet, that is the plane distribution of charge. If you consider the volume charge distribution like uniformly charged conducting sphere or uniformly charged non-conducting sphere, uniformly charged cylinder, in that case, at any point, you can calculate the electric field strength due to that charge distribution by using this Gauss law. Okay, so the Gauss law importance is you can use this formula for any either linear charge distribution or surface charge distribution or volume charge distribution. The first thing, the closed surface may be regular or irregular shape, any shape. It doesn't depend on size and shape of that closed surface. Okay, just by using the concept, symmetry concept, very easier for calculation of the electric field strength in that cases. Right, sir. Now, so let us go for how to derive the integral form of differential. This one, how to form the integral form of this Gauss law. We have to derive this one, right? So for that, I am considering the diagram. You see here. Here, very simple. This is a closed surface, right? A point charge plus Q is placed at point O. Okay. Now, on this surface area, I consider a small area element. This area element is the ds. Okay. Due to this point charge, the field strength at this point, this is the point P. In this direction, E bar. Already I told you, the small element is a vector quantity, area element. So what is the direction of this area element? That is outward unit vector, normal unit vector n cap. That is the direction of ds bar. Say that angle between n cap and E bar is theta. Right? Now I am joining this surface area element periphery. Here angle subtended by this surface area here, this is the d omega. D omega. This is the solid omega, solid angle. This is called solid angle. Okay. Now, so my question is, so here the total area is divided into small area elements like this ds like that. This total area is divided into small area elements. Now I consider small element, one element. So what is the flux through this ds? I am writing electric flux through small area element. ds is given by what is that? That equals to E bar dot ds bar. E bar dot ds bar equals to E ds cos theta. Okay. But here we have the so many number of area elements. Number of area elements are there. Okay. So by summing this, the total flux through the all the area elements, this is I am writing d5, flux through the small element d5. Then total flux, the total electric flux through the given closed surface, through the given surface, S is given by, this is the total surface area S, right? That is phi E is equals to integral over a surface integral d phi E, right? That equals to integral over S, it is E bar dot ds bar. Okay. Okay. So phi equal to surface integral E bar dot ds bar is E ds cos theta. ds cos theta, equation 1. Okay. But the field strength due to the point charge q at the distance r, this is the distance r. The distance of the point P from the point charge q is r. Field strength due to the isolated point charge at the distance r, E is equals to 1 by 4 pi epsilon naught q by r square. Okay. Substitute this here in the equation 1. Then what we get, then substituting that, the flux phi E is equal surface integral E bar dot ds bar, that equals to here surface integral E ds cos theta E 1 by 4 pi epsilon naught q by r square ds cos theta. Okay, right. So this is equals to, here you take this common, q by 4 pi epsilon naught right outside of the integral, 4 pi epsilon naught surface integral ds cos theta by r. Okay, but ds cos theta by r square equal to d omega. I am not deriving here. This solid angle d omega equal to integral ds cos theta by r square. So, but d omega equal to ds cos theta by r square. Okay. Now, substituting that in the above expression, we get 2 by 4 pi epsilon naught surface integral d omega. Right. So this small element is making angle d omega solid angle here. So then the total angle subtended at the point O is equal to 4 pi. Integral of d omega equal to 4 pi. Q by 4 pi epsilon naught into 4 pi. Where since integral d omega equals to 4 pi. So 4 pi cancel, right? So what left there? Therefore, phi total flux is equal surface integral E bar dot ds bar, that equal q by epsilon naught. So this is the required expression for Gauss. Okay. Here we consider only the charge q. The charge enclosed by the considered surface is q. So what we got? The flux through that surface is equal q by epsilon naught. That is 1 by epsilon naught times to the charge enclosed by that surface. Right. If there are number of charges are existing in the closed surface, q1, q2, q3, and so on, then we take the total charge q equal q1 plus q2 plus q3. If there are some positive charges, negative charges are existing in this closed surface, then you take your positive charges as positive, negative charges are negative. So net charge is equal q1 plus q2 plus q3 and so on. Right. So the statement is, again I am repeating, the total flux, the net flux or total electric flux through any closed surface is equal to 1 by epsilon naught times to the charge enclosed by that surface. This is the Gauss law. So this expression is called as integral form of Gauss law. It's very important question, semester point of view, and entrance oriented question also. Phi equal to surface in E bond or ds is equal to by epsilon, where Q is the net charge. You should remember that. Now, next, let us go for differential form of Gauss law. Deriving the differential form of Gauss law. Gauss. Okay, right. According from our previous discussion, what is the integral form of Gauss law? That is phi E is equal surface integral E bar dot ds bar equal to Q by epsilon equal to 1, right? But we have three types of charge densities: linear charge density, surface charge density, volume charge density. Linear charge density, we write it as lambda. Lambda equal to charge per unit length. We talk in the case of charged wire. The surface charge density is denoted with letter sigma, that is charge per unit area, 2 by E. In the case of uniformly charged plane sheet, the volume charge density rho is equal to charge per unit volume. We talk in the case of volume charge distribution. For linear charge distribution, we consider this lambda. For surface charge distribution, we consider this sigma. In the case of volume charge distribution, we talk about the rho. Here we consider the some closed surface area about the charge. So that the closed surface area bounded some volume. Therefore, we should consider the volume charge distribution. That rho is equals to dq by dv. dq by dv. Okay. So from this, dq is equals to rho into dv, integrating both sides. Integral of dq is equal to, that is the total charge q, equals to integral of rho dv, that is over volume v. Say equation 2, rho dv. Right? Yes, q is equals to, that I am writing it is small q. Integral of dq equal to q. Okay. So substitute this here. Then phi e is equal surface integral E bar dot ds bar, that equals to q by epsilon naught, that is 1 by epsilon naught into integral of rho dv over volume integral. From Gauss divergence theorem relates between surface integral and volume integral. So how we write? That is surface integral E bar dot ds bar is equals to the volume integral divergence of E bar dv. This is equation 4. Okay. Here E bar dot ds bar equal 1 by epsilon naught. Instead of q, I substituted integral of rho dv. But if surface integral E bar dot ds bar equal to volume integral divergence of E bar. Okay. From equations 3 and 4, you can write, right? From equation 3 and 4, right side just you equate. So what we get? That is volume integral divergence of E bar dv is equals to 1 by epsilon naught into volume integral rho dv. Right, sir? So then divergence of E bar, that equal to del dot E bar. Del is an operator. Del, you know, I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. Del is an operator. So del dot E bar, that equals to what is that? Rho by epsilon naught. Okay. So then taking cross multiplication from this, del dot epsilon naught E bar is equals to rho. Okay. But epsilon naught into E bar is we will discuss in detail in the dielectrics. Just I am taking the expression here. Substituting that, del dot d bar is equals to rho. So this is the differential form of Gauss law. Divergence of E bar or del dot E bar equal to rho by epsilon naught. Otherwise, del dot D bar, capital D bar equal to rho. So the divergence of the displacement vector is directly proportional to volume charge distribution. The divergence of the electric field, the divergence of the electric field strength is directly proportional to the flux or volume charge distribution. Okay. So in this way, we will derive the differential form of Gauss law. So till now, we covered the integral form of Gauss law. By using that, we derived the differential form of Gauss law. The third one concept we are going to discuss is how to derive the Coulomb's inverse square law using the Gauss law. Okay, the third one. So deriving Coulomb's inverse square law, Coulomb's inverse square law from using Gauss law. Using Gauss law. Okay, right. So for that, I am taking a point charge Q. So around this, I consider a spherical surface. This is at the point O. Right? Now, I consider a small area element ds on the surface. It is ds. The radius of this sphere say r. Right? Suppose that it is a point charge, positive charge, then since the line of force will be in this direction, hence at this point, the field direction E bar will be along this field line direction. Okay? What I'm saying? I consider a spherical surface of radius r about a point charge plus 2, which is located at the point O. Now, if you consider a point P at that, a small area element ds is taken. Then the normal unit vector at that point n cap will be like this. The angle between n cap and E bar is theta. Okay. Yes. Now I am writing the flux through this small element. Flux through electric flux through ds area element is given by d phi is equals to what is that? E bar dot ds bar. Already we discussed that. Okay. So here E bar dot ds bar that equal to E ds cos theta. That is equals to, since A bar dot B bar equal to AB cos theta. Using that, E ds cos theta. Right, sir? Now you consider the total surface, the total spherical surface area. Then flux through this total surface area, that is phi is equal integral over S d phi E. Phi E is equal to integral over S, that is E bar dot ds bar. E bar dot ds bar integral of S equal to E ds cos theta. Okay, it is cos theta. Equation 2. Equation 1. Right? According to Gauss law, the surface integral E bar dot ds bar is equal to what? That is 1 by epsilon naught times to the charge enclosed by that spherical surface Q. This is say equation 2. Equating equation 1 and 2, right? Look here. So that is surface integral E ds cos theta is equal to Q by epsilon naught. Q by epsilon naught. Okay, Q by epsilon. But what is the field strength due to the plus Q at this point? So from the point charge at the distance, our field strength formula 1 by 4 pi epsilon naught Q by r square. Okay. So here E constant, you write outside, or substituting that, what we get? Now I am dropping this. The surface integral, okay, surface integral E ds of theta is equals to right side 2 by epsilon naught, right? Here E right cos theta outside integral S ds is equal to 2 by epsilon naught. By adding all these surface area elements, we'll get the total surface area. So that is integral of ds is equal to total area. That is the area of the spherical surface 4 pi r square. Then EA, that is the EA of theta is equals to EA cos theta is equal to Q by epsilon naught, right? Look, EA cos theta equal to Q by epsilon. E into E what 4 pi r square cos theta equal to Q by epsilon naught, right? From this E is equal to 1 by 4 pi epsilon naught, okay? Integral of look sir. Here theta cos 0 1. Remember that cos 0 1. It is not cos 0 1. EA equal to Q by epsilon. Why? Because at this point n cap direction is in the same direction. N cap and E bar both are in the same direction. Just correction. Due to the point charge, the direction of field strength in this direction. So here we consider the spherical surface. Okay. In the case of symmetrical spherical surface, the flux is always normal to the surface. The lines of force are always perpendicular to the surface. Here the electric line of force is perpendicular to this area element. And where M cap is parallel to the ds bar. Area element is parallel to the E bar. N cap direction is parallel to the field direction. Angle between N cap and E bar is 0. So here cos 0, that is 1. Integral of ds is equal to A, EA equal to 1. E into E 4 pi r square equal to 2 by this one. Then we get field strength 1 by 4 pi epsilon naught Q by r square at the point P. Okay. Using the Gauss law, we derive the expression for electric field strength at the point P. How much we got? E is equal 1 by 4 pi epsilon naught Q by r square. Suppose now I am keeping a test charge there, Q naught. Okay, if the Q naught charge is placed at that point, then at this point field strength is this much. At the point P, we have this much of field strength. In that field, I am keeping the test charge Q naught. Then it experiences the force F is equal to Q naught into E, right? I hope you understand. At the point P, we got the field strength this one. In that field, having the field strength capital E, now I am keeping the test charge Q naught. So then, how much the force acting on Q naught? F is equal to Q naught E. Hence, F is equal to Q naught into this one by 4 pi epsilon naught Q naught by r square. This is the Coulomb's inverse law. If the charge Q naught is there, distance between point charges is r, then the force acting between Q and Q naught is 1 by 4 pi epsilon naught Q naught by r square. That is the statement of Coulomb's inverse law. Right. So simply by using the Gauss law of electrostatics, we derive the Coulomb's inverse law. Okay. Now, okay. So in the present lecture, what we covered, the concept of electric flux. So with this present discussion, so what is the importance of Gauss law? That is now I am going to explain. The Gauss law importance is, it is applied need not to be real surface. In most of the applications of this law, the imaginary surface considered that may be empty space or embedded in a solid body or partly in space and partly within a body. This is the point one. The second thing is, it is true for any closed surface irrespective of size or shape. You can consider either spherical surface or cylindrical surface or regular shape or irregular shape, small size or big size, whatever it is. It is useful for any shape of closed surface. This is the second thing, second important point. The third important thing regarding the Gauss law is it is oftenly used for easier calculation of electric field strength when the system has some symmetry. Okay, for example, linear charge distribution, surface charge distribution, or volume charge distribution like charged uniformly charged conducting sphere or non-conducting sphere. In those cases, we use this Gauss law, very simple for calculation of the electric field strength. And also, so whatever we are considering the closed surface around a charge, that surface is the hypothetical surface that is called Gaussian surface. Okay, the electric field at every point on the Gaussian surface either perpendicular or tangential. Remember this. The electric field strength at any point on the Gaussian surface that may be tangential or parallel. So the one more point is here the electric field at every point on the Gaussian surface that may be perpendicular or tangential to that. In the previous discussion, while we are deriving the Coulomb inverse square law, I consider the spherical surface around the point charge. There, the field strength is perpendicular to the Gaussian surface. Okay, in the concentric spheres around a point charge, they are the equipotential surfaces. In the case of equipotential surface, the field strength or electric lines of force always normal to the surface. Okay, so Gaussian and at any point on the Gaussian surface, field strength may be tangential or it may be perpendicular. You should remember that. The last point is the magnitude of electric field at every point where it is perpendicular to the surface has constant volume. Yes, it is also, I think you observed in this previous derivation. Okay, while we are deriving the Coulomb's inverse square law, there I consider a spherical surface about a point charge Q, right? So there at every point the field strength remains constant. So that's why in integration, I write the E outside of the integral. Okay, so whenever the electric field strength is perpendicular to the surface, then at every point on the surface, in magnitude remains constant. So these are the important things to regarding the Gauss law of electrostatics. Okay. So in this present discussion, the points to be remembered are the first electric flux. So what is that? The total number of electric lines of force passing through the given surface area is called electric flux. The number of lines of force crossing normally through unit surface area is called flux density, that equal to electric field strength at that point, right? Gauss law statement is the total flux emerging from any closed surface is equal 1 by epsilon naught times to the charge enclosed by that surface. Okay, the integral form of Gauss law is the surface integral, that is closed surface integral E bar dot ds bar equal 1 by epsilon naught into net charge Q. The differential form of Gauss law, we mathematically express it as del bar dot d bar equal to rho or del bar dot e capital E bar equal rho by epsilon naught, where you remember that d bar is the displacement vector, d bar equal epsilon into E, rho is the volume charge density, that is the charge per unit volume. From this expression, it is very clear that the divergence of the displacement vector is directly proportional to the volume charge distribution. Thank you.